Oh, true.
Like old school guy. It's not
Sorry, man. That's what I've been saying.
Yeah, I was going to finish up the thesis and conclusion, so but maybe we can have like a meeting to make sure we're on the same page.
I think we need
But in the Zoom session, you said don't finish.
That's just
Said we don't need to calculate. Because that's what I asked. That's one of the things I asked. So he said don't worry about that part. Yeah, that That's a good just like what kind of reiterating. Yeah. Data sets. I found one that has like a lot of examples on like using it and like describing it. So I think maybe we'd have a reference one. It's like housing. So it's like crime, based predictions and churches.
As a person, I was like, matter text, this is chances are, like, the client needs to be notified. Yeah. It's more like,
No, it's nice. I mean, there's nothing wrong with it.
And that's my day.
I think it's still like a, it's like we just ran yeah, it was pretty cool. It's sort of like a Roman Colosseum thing. Yeah, we got a big green one.
Yeah.
Yeah.
So welcome, folks. Nice to see some new faces here. And it's my pleasure to introduce Dr. Erin LeDell. She's currently Chief Machine Learning Scientist at H2O.ai. She received her PhD in biostatistics with a designated emphasis in computational science and engineering from Berkeley. Her dissertation is entitled Scalable Ensemble Learning and Computational Efficient Variance Estimation and was awarded the 2015 Eric L. Lehman Citation by the UC Berkeley Department of Statistics. Her research focuses on ensemble machine learning, learning from imbalanced binary outcome data, influenced curve-based variance estimation, and statistical computing. She is the founder of the Women in Machine Learning and Data Science organization and a member of the R Ladies Global Leadership Team. Before working at H2O.ai, she worked as a data scientist and founded Data Scientific Incorporated. And she has created an online course called Machine Learning with Tree-Based Models in R on DataCamp. Erin, thank you so much for coming. Welcome.
Are we doing both screens? Is that okay? Or just one?
Whatever you're comfortable with.
Okay. Well, just leave them both up.
They're actually up on these other screens as well.
Okay, yeah, a lot of screens. Okay, so thank you for having me. This is my second time giving a class lecture at Santa Clara University. So I've been in this building once before. Your professor has given me a little bit of background about what you have learned already in this class, but maybe I'll just kind of do kind of a survey to see what you guys are familiar with. So first of all, do you have a language preference, R or Python? And if you like both, you can maybe raise your hand for both. But I'm going to do some demos at the very end, and so maybe just if there's a language preference for R, raise your hand. Okay, how about Python? Okay, so that's not very strong.
The class was in Excel minor.
What's that?
We used Excel minor as the tool.
Okay, so no one really cares. Okay. So I'll also show you the web interface to H2O then as well. And then how many of you are familiar with H2O? Have you heard of it before now, I guess? Or how many of you have used it? Okay, cool. Well, hopefully you'll all see how easy it is to do machine learning in H2O and just never look back, really. So, all right. So I'm going to talk about what I call, or what people call, automatic machine learning today. And actually, this slide should be the first slide. But so this is kind of the agenda, and at the very bottom there's a link to a URL. So if you want to download these slides for later, you can do that. So it's tinyurl.com scu-automl. All right. So first, I'm just going to talk about the H2O platform because I think a lot of you probably haven't used it before, and sort of what it's useful for compared to other machine learning platforms. And then I'm going to go into just sort of generally what is the field of automatic machine learning. And then I'm going to talk about the H2O AutoML project. So that's something that I work on. It's pretty much me and one other person part-time. So this is kind of like the thing that I spend all of my time on right now. And then once I sort of show you what that is, then I'm going to give you a few tips on how to use it best, and then I'll go over a demo as well. Okay, so somehow this slide got mixed in the wrong place, but here's just a slide about what is H2O. So it's the name of a company, and it's also the name of software. So just to clarify, so H2O AI is actually the name of the company. And up until recently, we had just one piece of software that we would produce called H2O, so hence the name. And it's been around for about 6 years. And then these are three people that we work with at Stanford, Professor Trevor Hasty, Rob Tibshirani, and Stephen Boyd. So they're all pretty well known in the machine learning community, and so they're our academic advisors. And we use a lot of their algorithms in H2O. So GBMs and lasso regression are both by some of these guys. And then Stephen Boyd, we have one of his algorithms in there as well. So we're right up the street, I guess, in Mountain View. And yeah, so that's the company. We're about 100 people now. And up until, like I said, up until recently, the only thing that we did was produce this platform called H2O. We now also have an additional piece of software that's called driverless AI, which is actually quite similar to what I'm talking about today. So AutoML is sort of the open source version of that, although they're completely separate code bases, and driverless has sort of other components to it that AutoML doesn't have. So yeah, so H2O, the software is open source. And if you know anything about open source licensing, this means basically you can do whatever you want with it. So if you go off into the world and you're working at a company or you start a company, you want to look for software that's licensed as Apache 2.0. It means you can basically do anything you want with it. You can build, change one thing and sell it. You can do whatever you want with it. So business people generally care about that, and developers not so much. But so basically, it's a distributed machine learning platform, and what I mean by that is that you can run it on multiple machines. So one of the things that can be difficult about machine learning software is that you might run out of memory very quickly if you're trying to run it on your laptop or on even a single machine, because data sets can be really large. So the idea with H2O is that we've rewritten all the algorithms from scratch so that you can run it across multiple machines, and the way that your data is stored as well is across multiple machines. So if you have, like, let's say you're building a little cluster on Amazon, and each node has 16 gigs of RAM, and you have 100 gigabyte data set. Well, you need to spread that out amongst a bunch of nodes on Amazon. Or you could pay more money and get a bigger instance on Amazon. But at some point, I think Amazon has terabyte RAM is like the 1 terabyte of RAM is maybe the biggest machine you can get, and those are quite expensive. So what it was designed for is sort of cheap commodity cluster hardware like Amazon AWS or now Google Cloud or any of those sort of cloud platforms. So that's the idea, is you actually have to do a lot of work to rewrite the algorithms so that they work in this distributed way. And so that's sort of the value of H2O. There's a few other things that I'll highlight. So this is kind of a reiteration of what I've said, but let me sort of go into a few more details. So everything's written in Java, and sometimes people ask us, like, why Java versus C++? That just has to do with our co-founder was a sort of well-known Java guy from Sun in the 90s, so we went with Java. It's also still the most widely used enterprise language. But data scientists don't like Java, so we make that simple by having APIs in R and Python, and also in a web GUI. So if you're a data scientist, or you're a even like a junior data analyst, you're just new to machine learning, you don't even know that much about it, maybe you don't know how to code in R and Python, you can use the web GUI. But you can also, once you're typing a lot of code, your hands get tired after a while, maybe you just switch over to the web GUI. I do that quite a bit. And then the other thing that's unique about H2O versus other libraries, so it might help to compare against some libraries that you might know. So if you're a Python person, you might know scikit-learn. That's kind of the big library that has a whole bunch of algorithms and the infrastructure around machine learning algorithms. If you're an R user, you might use something called Caret or MLR. So both of those or all of those are really libraries that have a single interface to a whole bunch of algorithms. Because in general, you don't know what algorithm you might want to use, or you don't know which one's going to work well on your data. So you want to have a tool where you can try a bunch of different things and see what works. And so rather than having to, use a whole different paradigm each time you're trying out different models. So that's kind of the idea. And then this part is important to if you're going to deploy your model to production. And so that was the other sort of angle of H2O, was that we are a company, and so we need to make money, and we're giving away the software for free. So then maybe you guys would ask this: how do you guys make money? Usually somebody asks me that by the end of the lecture. It's an important question to know, I think, before you use anything or devote any time to a particular solution. So basically, we sell enterprise support for H2O. And so in order to do that, we need companies that are running things in production and actually care about H2O. So we make this sort of a priority to be able to take a machine learning model and put it into production is actually H2O is one of the few libraries that makes that very easy. And then this is just, where can you run H2O? Initially, it was, when it was first created, Hadoop was kind of the dominant big data paradigm. So this is 2012, which in like data science years is like, eons ago. But basically, Hadoop was really popular at the time, so we first made these machine learning algorithms so they would work on Hadoop. Then Spark came along, and that became really popular, and so we also, we actually rewrote everything from scratch at one point and made it work on Spark and Hadoop. But primarily, I see people just using it on their laptop if they're like a data scientist. So unless you need a huge cluster, it's easier just to run it on your laptop. And there's no difference in the way that the code runs or works. So it's pretty easy if you just want to prototype on a smaller data set on your laptop and then bring it over to some production cluster. So, all right, so those are kind of just some things that are unique to H2O when people sort of compare it to other libraries. So this will be the most, I guess, technical engineering slide. So this is just to introduce some concepts about H2O that if you're going to use it, they're useful to know these two things. So there's something that we call the H2O cluster, and you don't really have to think about what that is. It's just a Java process running on your machine, but we call it the H2O cluster, and that's where everything happens. So all the data is loaded into the cluster, all the models get trained in the cluster, and all of that. So, and just the reason I clarify this is because we use this to mean like a program running, not a physical piece of hardware cluster, but it would run on a physical cluster. And the way that it scales is you just add more nodes to your cluster. So if you have too much data and it's not able to fit on one machine, you just keep adding nodes until it fits. And then the other thing that's not too important to know about, but if you're used to doing data science, you're used to playing around with a data frame in R, Python. They're both called data frames. So this is just, if you're used to Excel, this is basically what an Excel notebook looks like as well. You have rows and you have columns. And the thing about H2O frames is that when you play around with them on your machine, it seems as if it's all just running on your single machine, but there's actually, the way that it's split up across machines is that some rows are on one node, some rows are on another node, and H2O figures out how to sort of take your queries. Maybe you want to shuffle the rows, or you want to subset the rows, or something like that. So you just write normal code like you would in R and Python to subset the data frame, and it will do that in a distributed fashion. So these are just concepts. You don't have to know them really to use H2O, but just hearing them once is helpful. Okay, and so just a little bit more about what the library offers you. So, like I said, H2O is just a collection of machine learning algorithms. So I think you probably have heard of the difference between supervised and unsupervised algorithms by now, and you're probably mostly dealing with supervised algorithms. So we have both, and here's some of the ones that we have. So GBM, which is probably, so gradient boosting machine, or GBM, that's probably the most powerful algorithm. Outside, so we could get into a big debate about deep learning versus non-deep learning right now, but for what I would call like regular tabular data with numbers or even categories in the data, GBMs typically perform best. And I say that, it can always be different, but that's in my experience and the experience of a lot of people, that's the case. Now, if you're wondering, like, I heard about deep learning, I thought that was like the coolest thing, and that's the most modern, like, cutting edge thing in TensorFlow. So just so you know, when to use H2O versus something like TensorFlow. So, so there's different types of neural nets that TensorFlow supports. So, and I've listed DNN, which stands for Deep Neural Network. So we have one type of neural network in H2O, and it's the kind that performs well on this sort of tabular data. But if you have image data or video data or text data, in some cases, text data you can also turn into the tabular data. But those are the cases in which you should be looking at something like TensorFlow. So yeah, so TensorFlow has like convolutional neural networks, recurrent neural networks. These are all more complicated neural networks that perform really well on those types of data. But that's, I think sometimes people get confused about which one to use or what's, you know, or thinking one is always good versus the other. But it really has to do a lot with the type of data that you're working with. So, so yeah, if you have images, convolutional neural networks are good. If you have sequential data like time series or text is also considered to be sequential data, then recurrent neural networks are good. So just so you're aware, so we're basically trying to do everything. I mean, we didn't design it this way because TensorFlow came after, but basically, if you have those two things, you cover basically all of machine learning. So it's good to know what tool is the right tool for the job. So, but in most like businessy type of cases, you end up seeing things that look more like what a database holds. So tables of data. Although if you work at a big tech company like, you know, YouTube or Facebook like that, you might have a lot of image data. All right, so that was kind of a tangent, but these are a list of some of the algorithms. So these are all acronyms. So this stands for random forest. That's another tree-based method similar to GBM. Also very good, but GBMs you can typically get better performance. Deep neural network, I mentioned. So GLM, which is sort of generalized linear model, that sort of most basic type of thing, where maybe some people wouldn't even call that machine learning, but it is basically the same idea. And then this is one of my favorite types of algorithms. It's called stacked ensembles or stacking or super learning. There's a lot of different names for it. But basically, I'll talk about that later. But that's when you actually use machine learning to figure out what the best combination of algorithms are, and then they all like combine their thoughts together and give you a better result than if you had just a single algorithm. So if your goal is like performance or model performance, then using a stacked ensemble is always better than not using one, basically. And so if you have heard of this website called Kaggle.com, how many have heard of Kaggle? Okay, so unless it's an image-based competition, everyone's winning Kaggle with stacked ensembles. So there's just no other way to win Kaggle. So, so if you want to be really competitive on Kaggle, one, you have to understand feature engineering, which is not a topic I'll spend a whole lot of time talking about today. And then you also have to know how to do stacked ensembles. So it's really easy with H2O. So that's a good tool to use if you like to Kaggle. And then this is all just sort of stuff that you have to do when you're doing machine learning that has to do with making your data in a shape that's appropriate for the algorithms. So these are kind of just sort of annoying like tasks that need to be done. So we just do all of that automatically in H2O. Yeah, so in other libraries, you'd have to like write the function to do that every time. They would have a function that would do this, this, and this, but you have to write all that code yourself. And then this is also a useful technique. So this has to do with when you're training, if you've ever heard of the term like overfitting your model? So that's basically when you train for too long and you didn't stop training when you should have stopped. So some models it's hard to overfit. So like a GLM, you can't really overfit a GLM. But GBMs in particular can be overfit very easily because you keep adding more trees and it keeps concentrating on the mistakes that it made previously. So if you keep letting it, sort of over focus on those mistakes, then it sort of memorizes the data too much, the training data too much, and then it doesn't do as well on new data. So there's something that we call early stopping, which is just a name for having some technique to stopping the model from overfitting. That basically just involves training a model. If it's GBM, you're adding trees, and that's the iterative process. So if you're training, basically each time you then test the model on a validation set, and then you train another tree, and you test on the validation set, and you keep going, and then you basically watch until the validation error starts to go up, and that's how you know that you've overfit. But we will do that automatically. So that's kind of a manual process, which if you're a data scientist and you're used to tuning models, you might want to do this by hand if you're, or you could let H2O do it for you. And if you don't do that, you'll probably still get like a decent model. It's just not going to be the best model that you could have gotten. So here's a bunch of other things that are related to machine learning but are not algorithms. So cross-validation, grid search, random search. So these are all, cross-validation, you've probably heard that term by now or know what it is, but just a way of measuring the performance of your model. And then grid search and random search are just choosing amongst a large number of versions of a model. So you could have like 100 GBMs and you try all the different values of all the different parameters, and then you want to choose the best one. So these are just two different ways of generating a bunch of models and then picking the best one. And so there's also functions to do that in H2O. And then all the stuff, once you have the models, every model has a sense of variable importance. So if you're just curious about understanding something in the context of your data, so what variables were important in this model, that's if you only care about performance of the model and nothing else, maybe you don't need to look at that. But sometimes it's interesting to just look and see which features were important. And then all sorts of different metrics that you can use. So yeah, so this is just a whole bunch of different things that you can do with H2O. Okay, so enough kind of about H2O. So I'll talk about just automatic machine learning now. Okay, so this is sort of, probably other people would agree with me on this, but this is kind of my interpretation of what automatic machine learning is composed of. So there's some different pieces. So there's sort of anything that has to do with preparing the data. And then there's, I guess I should say these are aspects of machine learning in general, but automating these is, when you have an automatic machine learning system, you need to deal with all of these things. So you need to deal with data prep, you need to create a bunch of models, and then this is sort of an optional piece at the end, but it's very good to do that if you care about performance of your models. There's all different ways of ensembling them, which means combining the models together into a single model. So I'll talk about a little bit more about what is included in each of these categories. So I already mentioned this stuff earlier, the imputation, which just means filling in missing values if you have missing values. One-hot encoding is a type of a technique for dealing with categorical variables. And some algorithms require that you do something like that and some don't. And then standardization. So some algorithms require that you normalize the features. And so, if you don't know what any of that means, then H2O is a great library for you because you don't ever have to learn. And you should probably, know what it is. But it's just, these are kind of like just sort of annoying things that you have to always deal with, and then it's nice to have them dealt with automatically. So other things that could be considered data pre-processing would be like feature selection. So maybe you want to just select some subset of your features. If you know, let's say you work at like a giant internet company and you collect like millions of data points on a person, then maybe you don't want to train your models with like a million features. Maybe you want to just kind of focus on some subset of those. So that would be feature selection. And then something else that's related is called feature extraction. So another way to, and kind of the difference between those is that feature selection, you're actually just taking a subset, whereas feature extraction, you're actually creating new features from the original set. And sometimes you do that to sort of shrink the dimensionality and then just use the new features and throw out the old. Or sometimes you might do that and then add them to the original as well. And then there's all sorts of things that I won't get into that are sort of really important for Kaggle. Again, like if you want to win Kaggle, all this stuff really improves your performance if you encode your categorical variables in a certain way. And there's all different ways to do it, and it's kind of an art, but also a little bit procedural, so you can automate some of it. This is particularly important if you have some column in your data set. Let's say it's zip code, and there's like 50,000 zip codes. So that's like a lot of granularity, and some algorithms will do what's called one-hot encoding, which actually blows that up into 50,000 extra columns. So if you're using GLM or deep learning, it has to do that. And so that's kind of like, if you have really what we call high cardinality categorical columns, like things will blow up and like you're like, why is my model not training? You know, like things get kind of crazy. And so there's good ways to sort of handle those high cardinality categorical features before you give them over to the machine learning model. And even if it's not deep learning or GLM, the tree-based models will also not like that very much either. So, yeah, if you look in your data set and you have some column that has like 1 million values that are not numeric. Well, okay, zip code is a numeric thing, but it's actually technically a category, but we won't talk about that. All right, so anyway, that's all data pre-processing stuff, and some of that, or most of it can be automated to some extent. And then the model generation, there's a lot of different ways, like I said, to create a bunch of models. One is called grid search, or to differentiate from random search, we might call it Cartesian grid search. And if you're going to do one or the other, I would say you should do random grid search because it's I don't know, I think it's better. So I won't go into details, but instead of, I mean, it's basically you find good models quicker when you're randomly sampling from your hyperparameter space rather than doing the whole, combination of all parameter values. So that's just kind of like a random approach. Then there's something that's called Bayesian hyperparameter optimization, which I won't talk too much about, but that's a little bit different way of finding a good model. So it's this iterative process where you train a model and then you have another model over here that helps you figure out what's the new set of parameters you should try. And then you try those and you report back to the other model, and then it learns something and it gives you another set. And so it's kind of this back and forth thing, and you can get to a better model in fewer iterations than if you're just randomly trying a whole bunch of stuff. But it takes more time if you can parallelize random grid search very easily. You could do them all at once and then you're done. But this one, you can't parallelize this at all. So you have to do it in a sequence, and so it can take longer, or and the software, the open source software for this is not that great. So yeah, so that's probably maybe something that we'll add to H2O at some point. We don't have it right now. And then I'll kind of skip over that, but So in the next section, so now you have a bunch of different models. So one approach is you can just say, well, what's the best model out of this group? And then that's my winner, and I'm going to move on and put that model into production and move on with my day. But usually you can actually get a better model by combining some, either all the models or some subset of the models together. And there's two kind of main ways that people do that. One is called stacking, which is the one that we use in H2O. And then there's another type that's more of like a greedy approach where you add one model at a time and you kind of keep adding models until it doesn't help anymore. There's not necessarily like which one's better. I think it depends a lot on the composition of your set of models, which one of these will work better. Okay, that was a lot of information. Does anyone have any questions? Too much. Yeah.
Do you typically find younger enterprises or startups that try and focus on machine learning using H2O a lot?
So you're asking like, do startups use H2O more than enterprise?
Like everything's about big data and ingesting all of this stuff. But my company is one of those. I work at a startup and we do cloud infrastructure management. So there's like petabytes and petabytes of data, and like for us, something like this could be potentially very useful instead of having to spend a year or 2 years developing our own ML models.
Yeah, I mean, a lot of people use H2O. The people that pay us are usually the bigger companies, so we know more about their use cases and what they're using H2O for. But it's really like, doesn't matter the size of your company. It's more like, what is the size of your data? Are you productionizing your models? Are you not? The one data scientist that you hired, does he already like scikit-learn? Is he using that, or she? So I think people are very passionate about what tools they use. So sometimes people might use a tool that could get them so far, but it's not. And especially in a startup, you're always like trying to just do what's right ahead of you, and you're like, oh, I just need, I already know scikit-learn. I'm just going to train some models, and then you start productionizing those models, and you start building more infrastructure on top of that, and then it becomes more difficult when you actually do want to, use bigger data to switch that over, and you end up kind of paying the price later. So I think. Also, learning a new tool is a cost. So if it's sort of like whatever your cost is at the moment, if you, it's pretty easy to use either of these libraries. With if you play around with them for like a week, you probably could do most things. So yeah, I mean, obviously I'm heavily biased towards H2O, but I also think that it's. I mean, I'll say the way that I got into H2O was being an R programmer and things not scaling. And so I was like this, and I was working on like developing all sorts of ensemble software in R, and it was just like taking forever. And I was like trying to graduate from my PhD. And so I was like, well, I could, have 2 more years just like waiting for my models to finish, or that's how I discovered H2O basically, is I was like, I need something way faster that I can iterate on more quickly. And because I wasn't writing any Java code at that time, so I could still use all of the H2O features just from R, like make my own little package on top of it, and you can do that with Python too. So I think like it's just how soon do you hit that pain point where you're like, oh, I need to start over and do something that's gonna get me, that has legs and I can keep.
So can I flip the question a little? Like,
yeah.
You said mostly it's larger enterprises that use it. What do you typically see them using it for?
Well, I wouldn't say there's more large enterprises using it, just that those are the ones that are our customers that we work with and we know about. I mean, they're using it for all sorts of things. So like, there's some people or some companies that, they have a user base and they have a model for each user. So they might have like 100,000 models that they want to retrain every single day. And there's just no way to do that if you don't have speed and scalability and all of that stuff. So there's people that are companies that use it because they get to train a ton of models quickly, and they need fast turnaround because like things are changing really quickly. Or there's people that just use it because it's easy to put it into production, and they know that once they put it there, it's going to be solid and it's not, it's not going to break because you have a new data set that has some new categorical feature that wasn't there before, and your software forgot to know about that and it died. So it's like things like that that people look for, I think. Or maybe you have a Spark cluster and you could choose between H2O sparkling water or the MLlib library, which is included in Spark. And I also, I'm going to just sound like a bad person, but that's like a bad library and you shouldn't use it. But I'm not the only one that says that. There's a lot of talks about that. And there's benchmarks too. So, and because I have such strong opinions, I need to like back that up by third-party claims. So one of the things that I'm going to be working on over the summer is there's a team of people or a organization called openml.org, and they focus entirely on benchmarking machine learning algorithms. And so I'm working with them and a bunch of other people. Like we're sort of working as a big group to do like really good benchmarks of AutoML systems, because there aren't really good benchmarks. And so, I could say H2O AutoML is so great, you should use it, but I haven't used every single other system, so I can't say for sure. But people have done pretty thorough benchmarks on just like random forest or GBM and like all the different like scikit-learn, R, SparkML, H2O. Yeah.
So you talked about the need of folks who need to retrain every day, but what about folks who just sort of looking sort of a one-off, trying to understand if there's enough in the data to be interested in it? Maybe in the small startup space that Varga was talking about.
Yeah, so I think that's actually where AutoML is really useful. So if you don't want to spend a lot of resources or engineering time or data scientist time, like experimenting on a whole bunch of different things, you can just just train one, or basically press a button or write one line of code, and it will do all of that like automatically. And so that will serve as a benchmark of at least what's possible. So maybe if you spend more time on feature engineering or maybe tuning the models a little bit more, you can even do better. But I think like my recommendation for anyone, especially if you're sort of like in charge of a data science team and they want to, somebody's like, oh, I love random forests and like I'm always going to use random, there's always like people who have very strong opinions. I think it would be like a good, just a very good like precautionary thing to do, to just try it on any AutoML system really, and just see where you're at, and then have the data scientists start from there. And then, because right away okay, this didn't work on deep neural nets, but it worked really well on random forests. So let's concentrate more of our efforts over there. I think like, yeah, there's a lot of like guesswork and a lot of people just do what they're familiar with and comfortable with, and maybe you work on a problem where that doesn't directly translate to money, and it's not a big deal if your models are just like not as good as they could be. But in a lot of cases, that's why people are using machine learning, is they're trying to make some financial gains in their product or their just the way that they do business. So I think it's just a safe thing to do is just try it on any AutoML system. I'll say, I won't even say you have to use H2O, just to get a benchmark of like what's possible. Yeah, so, and data scientists love to tune their models forever and ever and ever. and I love to do this too, but it's like, it's just like a thing, you know, you're like, I'm doing like real data science, I'm just like tuning, and you just wanna like be a perfectionist about it and spend like 2 weeks, and I would love to say that we should all let data scientists do that all the time, but it's actually very expensive to like let these people, you know, go off. I say these people, I myself included, because that's, you know, as if you're maybe more like on the manager or side or like overseeing a project, you if you don't put some reins on like the amount of time that someone can spend tuning and tweaking models, they'll just do it endlessly because you're like, oh, I think I can do better. Like, what if I ensembled this and this? And what if I did this? And you probably can make incremental progress, but at some point in a business, you just have to say like, okay, we've spent enough time on this, like let's move on to the next thing. So, okay. Is there a clock nearby? I'm just gonna make sure I'm not going over. Okay. Is it?
The red one.
Oh, yes. Okay, that's big. Okay, good. Okay, so now that you kind of know like what the field of AutoML is all about, and I should say, usually the goal in AutoML is like to get the best model in the shortest amount of time with like the least amount of effort, I would say. So that's generally what AutoML is all about. Okay, sorry, there's a few issues with the slides. I will update that. But anyway, so this is actually the same slide, but what I'm doing is highlighting the stuff that is in H2O AutoML right now. So, so the first bullet of data preprocessing is all already in H2O itself. So it's already, you get that for free in AutoML because all the H2O algorithms already do that. We might add something with feature selection, but in general, I tend to, I sort of almost prefer, unless you have like really, really wide data, that the algorithms sort of have exposure to all the features and then sort of not use the ones that are bad. Again, if you have 1 million features, you can't really do that, so you might want to use PCA or something like that before you give it to AutoML. But these are all areas that we can do more. This is something that we're going to add soon. It's called target encoding, and that has to do with anytime it sees a really high cardinality categorical feature, we will sort of handle that for you. And one thing I'll point out is that the driverless AI product that we have, which is sort of an enterprise, I don't know, I don't want to say enterprise, but it's basically the product that we also sell now. They really excel in this section. And so we have like hired a bunch of Kaggle grandmasters, and they know like how to do all this stuff. And so they have, that's when people say, well, what's the difference between this paid product and the open source one? It's like a massive amount of automatic feature engineering. So just because we, we have an open source version, we can't like 100% duplicate what's in driverless, but we will be adding a lot of target encoding stuff soon. So we just added target encoding into H2O, which is why it's not already in AutoML. So yeah, I think that's an area that will improve. And so this is all stuff that you can also do on your own. And I would recommend that if you want to get more performance out of AutoML, that you would focus on the feature engineering before you get to AutoML. So that's sort of what we have in data preprocessing. And then for model generation, we do a random grid search of all the different models. And then and we tune each of the individual models as well. I'm not going to go into details on that. But and then once we have this giant assortment of a bunch of GBMs, random forests, deep neural nets, GLMs, all these things, then we do stacking at the end, and we do 2 ensembles. So one is just a stacked ensemble of all the models, and that's usually the best one. at the end. And then we do a second one that is just the best from each of the different algorithms. So the best GBM, the best random forest, the best deep neural net, the best GLM. And the reason that we do 2 versions is because if you have 1,000 models and you want to take that into production and you have 1,000 model ensemble, that's going to be a little bit slow. Like, I mean, it depends on what your needs are, but if you need like sub-millisecond prediction times, you're not going to get that with a 1,000 model ensemble, because each of the individual models first have to make a prediction, and then they, put those into the ensembler, and then that gives you the final prediction. So we basically have the best model that we give you, and then a sort of production-ready ensemble that just has 5 models in it. And there's really not a huge difference between the 2 often. So if you're really, if you want some sort of compromise between performance and, speed and model performance, then I would probably recommend that you go with the 5 model ensemble. So that's just, sort of keeping our enterprise group in,
And when you give this talk in 5 years, where do you think you're going to be more interested? Is it going to be in that feature selection extraction row? Do you think?
I mean, there's a lot that you can do in each of these categories. So I think the biggest bang for your buck is here. But once you've kind of tapped that out, then you probably would focus a little bit more on this, like in combination with random grid search. And I'll talk a little bit about why I prefer using random grid search when we're doing stacking versus this. Even though in theory you get to better models more quickly through this process. So I'll mention that in a minute. But yeah, I think where we're going with it is we're looking into adding Bayesian hyperparameter optimization. We're looking into genetic algorithms as well to do a bunch of different things. So genetic algorithms can help you generate features. They can help you generate models, and they can help you generate ensembles too. So that's another direction that we'll go in, I think. And I mean, just in terms of practical stuff, I think that we want to do more with time series. So stacking is not really the way that the traditional way to do stacking. You can't really do it with time series data. So there's like a variant that we can do that will work with time series. So I would say supporting more data types would be another thing, like just easy stuff to deal with text, because we have sort of some tools to do that in H2O already, so that you could just give it text and it would handle that. Okay, so any more questions? Okay, and so I'll just mention, okay, so I said I was going to mention why do I like random grid search and stacking, because stacking does really well when you have kind of like a diverse assortment of models. And so one way to get diversity in your group of models is to just randomly generate models. So that's like, it's easy, it's straightforward, and it's already in H2O, and so is stacking, so it really all works well together. And this is kind of more specifically what's going on there. Basically, diverse or different models, when we're looking for diversity, we're looking for models that kind of fail in different ways. So some models might do well on this type of data, some do well on this. And so, yeah, you want to have models that sort of fail in different ways, or make uncorrelated errors would be like the statistical way of saying that. And then I mentioned that how stacking works is it uses a machine learning algorithm. So you could use any supervised machine learning algorithm. Typically, we use a GLM actually. So stacking sort of learns what the best combination of these models is. And if you're using a GLM for the meta learner, then you can kind of think about it as just a linear combination of these base learners. And so, yeah. And so that's different than just sort of averaging them all together or just kind of like looking at them and saying, well, I'm going to do 0.5 random forest plus 0.4 GBM plus whatever, and then add them all up. So I'm going to skip this part, but I'll leave it in the slides so you can sort of research it later. But this is just how stacking works. But I don't want to spend too much time on that. Okay, so this is just a reiteration of all the pieces of AutoML and H2O. So basic data pre-processing, then training a random grid of all these different algorithms. And so when I say using a carefully chosen hyperparameter space, so this is something that's actually pretty hard for a novice data scientist to do. So you have, first of all these parameters for the problem. So let's say you have a GBM. So there's maybe like 30 different things that you can tweak. So there's column sample rate, max depth of the trees, number of trees, row sample rate, like all, learning rate, all these like numbers that you don't know what the values should be to be best on your data. And so even just selecting which one of those you should try out takes knowledge, and then knowing what the ranges are. Like for learning rate, should you choose 2 or 0.001? Like what are good values? So all of that comes with like just experience as a data scientist, and it's like just a hard thing to teach somebody. You kind of just have to learn. There's not like a book that says this parameter should be this, because it's not that simple, because sometimes it should be this, but maybe it's conditional on these other things happening that you kind of have to know about, or maybe if your data is really wide, you might want different situations. So this is all like, so what we've done here is just take what we know about these values and these ranges and just put them in there so that you don't have to think about it. So, and maybe if you designed the grid space, you could do it a little bit differently and maybe you get a better value. It's, we're just going with like what we think generally does well on a lot of different types of data. So this part is actually more complicated than it sounds. I'm just saying, oh, train a random grid, like whatever. But you have to think about what parameters you're doing and like all the, yeah. So it's, so it can be a little bit complicated. So, and this is something that we can also improve over time. Like if we spend more time on benchmarking AutoML, we can test out tweaking these ranges and see how that affects. Like if we, run it on 1,000 data sets and we say, oh, if we moved this a little bit over here, it actually does better overall. So let's change that in a future version. So this is kind of like the sort of not secret sauce, but like stuff that you have to get out of a data scientist somehow. And then just tuning the individual models as well is something that happens. And then I mentioned the 2 types of ensembles. These are the 2 names that we use. Like one's called all models, and then the other one is called best of family. So that's the one where it's like the best of each type of algorithm. And then once you're done, we can just look at the performance of all the models, including the ensembles, and then rank them in a leaderboard. So leaderboard, that kind of term comes from Kaggle too. It probably predates Kaggle, but yeah. So this is basically it. You give it your data, and one thing I haven't talked about, well, let me see what's on the next slide. Yeah, I'll talk about some of the other parameters that you can use in AutoML. So this is basically with our web GUI, what AutoML looks like. So you can just give it a name if you want, so you can keep track of it better. Then you just select a data frame or training frame that you've loaded into H2O, and this is your training data. And then the way that you tell AutoML what to do, since it already knows what to do. You just tell it how long you want it to do it for, basically. So if you don't touch anything, it will just run for an hour and then stop. But maybe an hour doesn't, it's not enough, or maybe it's way too long for your data set, depending on the size. So you can change this time period. But maybe instead, you don't want to work with time, you want to work with number of models. So you could say, build 100 models and then stop. So if you want it to be reproducible, it's better to specify the number of models, because if you run it once on a shared machine, there might be a certain amount of resources available, and then if you ran it a second time, maybe it would be able to do more or less given that amount of time. So, and then these early stopping parameters, you don't have to touch those, but if you want to tweak it, you can. So the goal with AutoML is to do everything automatically, but also to let the user to tweak things as they want. So in the future, we'll also be able to let the user add specific models or specific grid searches to the AutoML process. So right now, you can tweak some things, but you can't tweak everything. And I think this is missing, well, I'll talk a little bit about some extra parameters later, but this is basically, if you're an R person, this is what it would look like in R. And like I said, you just point it at your data, and then you need to tell it like which column is the column that has the thing you're trying to predict. And then, tell it to run for, this would be 10 minutes. And then this thing up here is just, you're starting the H2O cluster. So you don't have to know anything about that. You just have to know that you have to run that command. And if you're trying to run it on a cloud system, then you would have to put in like IP address and things like that. Yeah.
Is there any, just as a general question, is there any pushback from people in your industry because of the current job security that exists from all the tuning that's required that you're kind of going away?
I think that maybe there's some people that are afraid of that, but I think for the most part, they would see this as a tool that makes them more efficient. So it's like, oh, if I know how to use this, then I'm going to be more efficient than that guy over there. And so I'm going to get better models than them. So it's kind of like an arms race, I guess. But, I think a lot of the reason that I had this idea to do this was because I was sick of writing the same code all over again. Like, I would just always write, huge random grid searches and then ensemble them together, and I was just writing the same code over and over and over again. And I was like, there needs to be just a function to do this. And this is just my personal interpretation of what AutoML should be given the constraints of H2O. And I mentioned there are a few other open source projects. So there's not really a whole lot in R. There is in Python, there's something called AutoScikit-learn. Well, it's called AutoSklearn. And so the AutoML community is like not very big. There's like 10 people basically. No, I mean it's bigger, but like there's maybe no more than 10 separate projects. So we all kind of like know each other and what we're doing. And so that's kind of another reason why we want to come together and do all this benchmarking, because it's like, well, you tried this whole strategy, does that actually work better? Or maybe I should add that to my AutoML, and I think they'll all sort of converge at a certain point. And then you'll have the different idiosyncrasies of the different projects. So H2O is really good for certain things, and then maybe other ones are good for other things, and then you just use the whatever AutoML tool that you want. And then if you're really like a hardcore data scientist, then you peel back the layers and try more things beyond just the AutoML function. I mean, your goal as a data scientist should be to beat this function. Like that's the starting point now. So we have a starting point, and then you should try to beat it if you can. Okay, yeah.
Branch off that same question, I heard on a podcast, an economist was saying the cost of all this is coming down, which is essentially what you're doing, the cost of tuning and doing predictions coming down, and in economics, what that says, you're gonna consume more of that, so we'll consume more prediction.
Yeah.
Would you agree with that standpoint, that basically someone who's currently doing the manual tuning, as long as they learn to use the automation, basically, they're gonna have plenty of work to do coming down the pipeline?
Yeah, I think so. I mean, data scientists will be the last job, right? So like, once all the jobs are automated, it's like the last one left. So it's still not a bad place to be, you know.
Flip the final switch, right?
Yeah, I mean, that's the same argument that they say about like, oh, well, all the AI is gonna take all the jobs, and then people claim, well, we've had this happen before, and like, basically the jobs just change and like people get new jobs. But you know, maybe we could hope in a utopian world that eventually there'll be no need to work and we can all just play around all day. I don't know, but maybe there'll be more jobs. I don't know. Probably for a while. So yeah, I think just making sure that you have the most efficient set of tools is the way to sort of be the best data scientist. And also, yeah, I mean, and just knowing this tool would be enough in a lot of cases, but if you want to be able to work efficiently with large text corpuses or image data, then you have to learn the tools that work really well in those things as well. But there's so, you know, you can get pretty far with learning like kind of one main tool, and then, yeah, I think most data scientists don't need to use 6 different tools every day. Kind of focus on one, and then maybe if a new project comes along in the future, they kind of try out some different techniques and shift over that way. But yeah, I would say like all of the open source machine learning libraries are working on something like this, because now that this exists, now that everybody has to sort of make it as easy as this. So yeah, I mentioned like in the scikit-learn world, they're working on a couple different projects there, and in R, they're doing some stuff as well, but it's a little bit more focused on tuning individual models using Bayesian hyperparameter optimization. So yeah. And actually, so in the TensorFlow world, there is a tool by Google called AutoML. It's not something that you can really just go and use. It's like a service on Google Cloud, and right now the full name is Google Cloud AutoML Vision, because it only does one thing. It does computer vision. So it's basically, so when they say AutoML, that's actually what they mean. It's kind of very different from this. And so yeah, if you have a set of images and you're trying to train an image classifier, you can use this service. You I guess pay some money. I'm not sure if it's open to everyone yet. It might still be in beta. So any day, maybe they will open it up to the public. But and then what they do, their AutoML basically automatically figures out what the best neural network structure is. So for your set of data. So that's where the computer vision community is heading as well. So yeah, everybody's kind of trying to do AutoML now, I think. So I think that's probably a good thing. Okay, and then if you're a Python person, same concept. Just start your H2O cluster, upload a data set into the cluster and call it train. And then, so also one thing you'll notice is there's no validation frame or test frame or any of that here. So you don't have to think about that either. So we will chop off a piece of your data to be a validation frame. So when I kept mentioning that you individually tune the models to make sure they don't overfit, that's what we use the validation frame for. So you can specify a validation frame if you want to have more control, but if you don't set anything, it will just do that automatically, and then it will rank all the results based on cross-validation metrics. And so for like a binary classification problem, we will just choose what we think is like the most appropriate metric and sort based on that. Of course, you can change that as well. If you have, if you want to sort by log loss instead of AUC, you can change these things. Okay, and then what you get back basically is just a data frame that has a list of all your models. It might look something like this. So, so this would be like what you get back in a binary classification. You get 2 columns. One is called AUC. That's a metric that people use to rank, sort of to score the models. Log loss is another metric. And which one you choose will also sort of, is kind of a decision by the data scientist, what makes more sense. If you can correlate one of these specifically to like the business problem that you're trying to solve, that's like the best way to, you know, decide which model is the best. But in general, AUC is good if you just need to kind of rank everything in a certain order. Like let's say you're trying to do like fraud detection and you just want to get like a score for each of your, you know, each of your credit card transactions, and you want them to, well, that's actually not a great example of using AUC, but people do use AUC in that case. A real canonical example is, let's say you actually want to rank your results like in a search, like your Google, and you want to rank like, what do I think is the highest, most likely like search result, that goes on top. So then you know, the next highest one. So if you think about what search is, it's actually each one of those links is getting some, you know, score, and whatever the score is the highest, that's like the first search result in the, you know, and it's answering sort of a binary prediction problem, like, is this link relevant to you? And so then it gives you some sort of score for how relevant you think it is. And the same thing is happening in fraud. It's like, how fraud-ish is this thing? And this is the highest fraud. So if you're like working at a, you know, company that has to detect fraud, then, you know, usually, you know, they would probably automatically flag a certain, like everything above a certain threshold as like definitely fraud, and like everything below a certain threshold is definitely not fraud. And then you have to kind of like deal with the like questionable ones in the middle, and maybe you have like a person look through those or something if you can't automate that. Anyway, I'm not going to really talk about what the difference is between these two things, but if you, if the actual scores need to be meaningful, then log loss is better, and if it's just the ranking, AUC is better, or is, you know, sufficient, I guess. Anyway, so what you see here is real scores on a real data set that I ran, and stacked ensemble with all the models did the best, like we would kind of expect. And then the best of family stacked ensemble is a little bit less than that. And then we see a bunch of other models here, like some random GBM is also really good, but not as good as the ensemble. And then we get some other GBMs. These are both random forests, but they're different versions. So this is just a regular random forest where we say DRF. XRT stands for extremely randomized trees, so it's like a variant of random forest. And then GBM, GLM, and deep learning either didn't make it into this run, or it's just cut off. I don't remember which one, but we kind of allocate a certain amount of time for each of these things. And we give most of the time to the GBM grid because we feel that that's going to yield the best results, but we also give some time to deep learning grid and random forest and other things. Okay, let me just give you a few tips. This is, Okay, I already talked about this, the training frame, like if you just give it a training frame, it'll break off a piece. And I wouldn't recommend using, there's another argument called leaderboard frame where you can pass a data frame specifically to score the leaderboard, but I wouldn't recommend that. Oh yeah, so I didn't mention this before, but one of the customizations that you can make as a user is you can turn on and off certain algorithms. So if you think you know what you're doing and you're like, I don't want to have trees, I only want to have GLMs and deep neural nets in my AutoML, then you can turn off the GBM in random forest. Or if you, and the reason I give these two examples is these are kind of the typical things you might want to do. So, conversely, if you really know that GBMs and random forest do really well, you might not want to waste any time on deep learning or GLM. So you can turn on and off things, but we'll do them all by default, yeah.
Do you have guidelines for flagging very shallow data sets where you just feel that there's insufficient data to even get started?
No, but we might want to do that. But I mean, I would say that if you have less than, let's say, like 1,000 data points, you might not get very good models. And you will notice that the stacked ensembles won't do very well unless you have probably at least 1,000 data points. But even if you have 500, you can probably just try it and see how it goes. There's no real cost to trying it out. And another thing is like deep neural nets take more data to do well. So if you only have 1,000 rows, you might see the deep learning kind of not doing so well. But if you have 100,000 data points, then it's fine. But that's all very difficult to make heuristics about because it's kind of like how much signal is in your data to begin with. And so if there's a strong signal, maybe you don't need as many rows. But if it's kind of weak, then you might need a lot of data. So it's hard to say, but yeah, so it's good just to give it a try. And I mentioned that it defaults to running for an hour, but that's not usually like what we would recommend doing. We would say, if you have more time, run it longer, but maybe just to try it out, just, even for like 5 minutes, just try it out and see what happens. I mean, a lot of this depends on the size of your data too. So, and so speaking of like the size of your data, so one of the arguments that you can set for the H2O cluster when you initialize it is something called max mem size. It's just how much memory do you want to give to your cluster. And if you have a lot of data, you will have to give it a lot of memory. So the rule of thumb that we tell people is basically, I mean, for AutoML, I would say you might want to have more memory because you're creating a lot of models, but sort of to train a single model, just the act of training it, you want to have probably like 3 to 4 times the amount of memory as the size of your data. And I mean, you'll know pretty quickly if it doesn't work. So, but the default for this is 4 gigs because we don't want to like blow up anyone's computer basically. So if you're dealing with like moderate to large data, you're probably gonna want to specify this thing. And you don't have to think too hard about it or know much about computer memory or anything like that. Just keep making it bigger until it works, or make it really big and bring it down, So just like play around with it. And you'll see, if you know how to sort of check how much memory is running on a machine at a given time, like you can kind of see what's going on. Because you might make it huge and then it only needs like 10 gigs, and so you can make it smaller. Okay, so this is like everybody's job in the future. All right, I won't go over this too much here. This is just tips about like if you want to run it for a little bit and see how it goes, then you can use the same project name, which is just an ID, and then extend the AutoML run. So you don't have to start all the way over. And if you were using a random seed and you started it over and did the same thing, it would just train the same models over again. So that wouldn't be that useful. So if you want to just try it out for a little bit, run it for 10 minutes, then run it for 10 minutes, and then you just run it again. As long as you put the same project name, it'll continue and add new models rather than starting over. So that's just kind of a, a tip about using it efficiently. But again, if you set the same seed 2 times in a row, it'll just duplicate the model. So you want to make sure you don't do that. And you'll maybe do that once and then see the models are duplicated by the scores, and then you'll realize. And then, so what you get, remember, is just a list of all the models. So if you actually want to save a model or save the ensemble model, then, in H2O, we just have like save model functions, basically. And there's a couple different ways you can save models. You can, if you're kind of just a data scientist and you're just running these for your own purposes, you can save a binary form of the model, and that's the easiest thing to do. But if you want to take it to production, you can save a different version of the model, which we call either a Mojo or a Pojo. Pojo stands for plain old Java object, and Mojo, I don't know. I mean, it stands for like model optimized something something, but we just thought that sounded cool. So, well, some person did. And yeah, and so those are the ones that are basically Java. Basically, it's just a Java file, and that you can then take and put it into production. Okay, so I'm just going to point you to where this tutorial is instead of kind of like walking through all of it, but this is, so on H2O, on the last slide, actually, I'll give you like all the links that you need, but one of the links is called slide decks, and that's why you'll see these slides, but then above that is tutorials, and so we have all different like tutorials. So there's AutoML tutorials there, and this will bring you right in the tutorials section to where the AutoML stuff is. And then this will kind of describe a few cases. So we have a binary classification example where you try to predict whether or not a product will be on back order in the future. So that's like a pretty standard like industry type of thing. And then that's in R and Python. And this specifies like some of the things that we go into. And then in the second one, we try to predict the output in megawatts of a power plant. And that is a fun problem because somebody wrote a paper about this, and with running AutoML for 30 seconds, we beat the paper like instantly. So that was pretty satisfying. I can't remember like how old the paper is. If it's recent, I would feel bad. It's 2014. Yeah, 2014. So, I mean, they had all the same technology that we have here, like GBMs, et cetera. But, so, if you want to make a hobby out of going around and like beating people at their publications, if you're just kind of a, that type of person, this is something you can do. So anyway, that's just what you'll see there. And then maybe I'll just show you one thing here. I just want to show you what an ensemble kind of looks like visually. So I skipped over the code, but basically you're training an AutoML, and then you get this leaderboard, and we're going to look at we're going to kind of look inside of the ensemble to see what's going on there. And this just shows you how to do this. So maybe I'll make like a function to do this a little bit easier in the future, but what you can do is you can look at kind of how the ensemble sees the contributions of each of the individual models, because all of the H2O models have variable importance, including the GLM. You can see how important the variables are, and in an ensemble, the variables are really just the base models. So it will sort of rank how important each of the base models, and the base models are just the models that go into the ensemble. And it will show you kind of how they compare to each other. So here's just a sample, or an example of an ensemble that we trained, and it thinks, it's feeling like this extremely randomized tree model is the most important, followed by this particular grid GBM model, another GBM, then the other random forest. And then we see down here, like, it's just completely ignoring the output from these two models. So it doesn't want anything to do with them. So that's like why it's okay to put in all sorts of models. Maybe some of them are really bad, some of them are really good. When you use a meta learner or the ensemble part, it learns to ignore stuff that's bad. So there's some computational cost to putting them all in there, but it's a safe thing to do. Yeah.
Can you select which one you need to use?
So if you want to get worse performance and just pick a single model, you would pick the best one. So let's say for some reason you're like, I don't want to use an ensemble, it's too complicated, or it takes too long, or something like that. You would just, I would probably not choose it based on this. I would just choose it based on the leaderboard above. So just like all the other types of algorithms, you can turn off ensembles if you don't want them. Like let's say you have time series data, you can basically control the way that the train and the validation set is, so that the training set is far back in time and the validation set is above that in time, and then turn off the ensembles, and then you can kind of do like time series stuff with AutoML. Yeah.
But can you select the models for ensembles?
You can't really, with AutoML, you can't select them because we've just said go off and to AutoML, go train a whole bunch of things and then put those in there. If you want to have more control over your ensemble, then you can just go learn about how to use the stacked ensemble function. So if you go to docs.h2o.ai, that's our documentation page. I should show you this anyway. And then user guide. And then if you go to algorithms, you'll see all the different things there. XGBoost is a kind of like a famous piece of software that's like really popular on Kaggle. It's a particular version of GBM, and we have just added that into H2O now. So, if you can't beat them, like join them or something. I think something like that. If you can't beat them, put them in your software, and so then, so now we also have XGBoost in there, which we'll be adding to AutoML too. So that should actually improve performance as well. So my point was, go to stacked ensembles, and you can scroll down and see how to, this will just give you our Python code, but it's pretty easy to use stacked ensembles in the GUI as well. And then you can just figure out what models you want, and then you can stack them individually. So that might be even something that you would try with AutoML afterwards. Maybe you'd say, maybe I'll try to make my own ensemble. And so you already have all the models trained, and you just access them by their ID. And then you just say, stacked ensemble, I want you to train these ones together, and then you make your own ensemble, and maybe you can do a better job. One thing that we're working on is a way to kind of pick the optimal set of models, because even though the one with all the models does the best, there's sometimes cases where if you put really bad models in there, it can kind of screw up the ensemble. It's hard to do, but it can happen. So, or maybe you just, want the best model of 10, or best ensemble of 10 models for whatever reason. So we want to develop ways to do that, but that's sort of like research right now. But it's all stuff that we can do, just takes time. And then if you just, go to h2o.ai/download, then you've got all the different things that we have. This is where you download it. But if you're like a regular R Python user, you can just download it. With Python, you do pip install h2o, and in R, you would do like the cran h2o package. And if you want to just run the GUI and you don't want R, Python, or anything, then you can get that from here. And this is basically, you just have to start H2O as a Java process on your machine, which is actually not that hard to do. You just type java-jar H2O jar, and then that would start up a web server at localhost port 54321. Oh, I'm not running it, but let me show you. Oops, I think I forgot to, oh no. So I'm just gonna start it from R, and then if I go here, then it brings up this thing. And you can use both at the same time. So if you train some models from R, you can go to Flow and like click on the models and look at them. And then to do AutoML, you just do that. To load your data, you can do, it's pretty straightforward, like loading data. And then, so I'll just leave the last like -1.5 minutes for questions. If anyone has any questions, like business questions are fine too. Yeah.
What's sticking with me is that you said something, there's different libraries for algorithms and some are better than others. So what makes a good library versus a bad library? And this benchmarking thing, why and how is that important?
Okay, so what makes a good library? I think where you can do basically everything that you want to do very easily and very without typing a lot of code to do that. So and then having a lot of different options, so different algorithms really is, and the ability to do all the things that you need to do that are sort of supportive of machine learning, like cross-validation or grid search or evaluating the models after the fact, or visualizing the models or things like that. It's just nice to have everything kind of all in one place. And so, because there's a cost to learning any tool, so you want to make sure that where you invest your time is not going to lead you to dead ends or have you have to hobble together a bunch of different tools to do it. And then the benchmarking, I think specifically for AutoML, benchmarking is really important because we are just like coming up with this stuff. We're like, maybe this works, or maybe we should do this, like based on my experience. So we want to make sure that when we're adding new stuff to our AutoML algorithm, that it actually is improving. So maybe we just tested it on a few data sets and it looked like a good thing to do, but then we forgot about all these other types of data sets or this and that. And so we kind of don't want to like overfit our AutoML system to like a particular type of data or a particular thing that like I know or my collaborator knows. So we need to know that this works generally for like everyone's problems. And so if we even make one little tweak, we want to make sure that's actually helping instead of either not doing anything or just creating more time that's not adding any value. So that's why it's like, because we have infinite flexibility on what we can add to this. So it's like we need some way to kind of measure our progress. And we want to do it so that benchmarking is really, really hard to do for your own software because you know your software better than anyone else, and you don't know the other people's software as well. So there's a tendency for people to like see what they want to see, or like not try as hard on the other stuff, and like we want to be more truthful with ourselves about benchmarks. So that's why we want to do like a collaboration. And so there's a term that we, I don't know who coined it, but it's like benchmarketing. There's like a lot of that where they're like, hey, look at our algorithms, they're so great. Like we benchmarked them over here and like they're so much better than all this stuff. And it's, you know, some of that is just people being dishonest, and some of it is like, well, they just did the best they could and it wasn't very good. So they should have, you know, talked to these people with their library and really figured out how to use it properly, and then really done like a collaborative benchmark. Yeah. So you see that a lot, people benchmarking.
More questions, folks? Erin, thank you so much. Really appreciate it.
I brought some stickers if you want some. Guess I'll just put them on this chair.
He's covered his door with stickers.
Oh, yeah.
So I guess,
about our thesis. It's really just not going to work if we just go through
They know.
I mean, I was looking at yours, right? And the heat map definitely helps too, because you can see like
Yeah, I mean, to be honest,
high volume, high price.
Yeah, I know.
somebody for sure. So,
I'll let you know.
so
Yeah, I think we'll try and write like the massive version. Just like the theater that's getting
we haven't wrote out.
I don't know how
well, feedback on the first one, we wanted to work
You guys can check out and find out. But I think our focus this week is basically to make the PowerPoint, because he said that.
so we can figure out what associates.
There's no paper's not due till like the paper's due right now.
streaming everything. I'm going to ask you for an MP3.
Yeah, but
There's been some folks who are online.
yeah.
That was our original thesis. We were hoping that there would be some episodes.
I mean, once we have the size together, we can do more like.
Did a button next for the next course. We do away with all the stuff we did, and just a long-term button, and we're done.
Just press the button. I like the sound of it.
Part of the problem is.
Actually, Grant, you had a quick question about A3?
Yeah. Oh, yeah, the business case part. So you just want to run
Oh,
that by
yeah,
it.
right, it's individual, so we'll just all do it.
So we have a bunch of data.
We can obviously.
But it's
put
somebody
it
else is doing it too. It's the data from Illinois for like alcohol sales. Okay. Iowa for alcohol sales. So we trimmed it down. It was like 10,000 rows.
Probably doesn't make sense.
Sure, it was better than that. So we took that down a lot, and the business case we're thinking of is clustering it and a targeted marketing campaign based on like zip codes.
Probably not zip codes, because that's our business case.
I
think our idea was
How many zip codes are there?
Think about it.
I don't know. I mean, I don't know.
Don't get your hopes up that zip codes are going to be the key differentiators. Other habits.
The idea was separating zip codes out to begin with, get the clusters, and then see if you can find any correlations.
How associated are they?
Yeah, see if we can find high spenders, basically.
The associations together.
Inevitably, you kind of time have to go to that thing that she was talking about where you plug one encoding, where you give a binary for each subcode and it just blows you up?
Yeah.
So that's what I said. I don't think
Everybody, yeah, that's basically.
Focus on our stuff. We're not
Cool.
we
Thanks.
have a little more time to get some information specific progress. We're not gonna, I don't think we're gonna be able to make too much progress on the paper tonight until we rewrite the policy.
Well, Jack, why don't you and me stay tonight, or I can stay. And Parker, I'll email
I'm
us.
happy to work on it, I just need a mouse around.
Okay, I have a.
I just don't know where we're trying to get.
So we could do.
Yeah, from 8 to 9 tomorrow.
Okay, so maybe like 6 to 7? Is that too early?
I can probably make it home by then. Maybe.
Do you want to do? We could also do like
I don't know.
9 to 9:30.
But
I mean,
I think we'll figure it out.
I'm comparing that
Work
to
is
the
interesting for me because
Yeah.
it just takes like an hour and a half to get home. So I
Oh,
have to-
really?
But I haven't found
Is that
any
in our-
explanation of
I'm in
how
Menlo
you-
Park. I have to drive over Dunbar, so it's like it's really
Yes,
clogged.
yes,
It's
it
really
says that
clogged.
you update all
Just
the
do the
way
92 to
at the
Hayward,
same
that was
time,
like-
but I haven't found
That's
out
even
how
worse.
to-
That's even worse.
how to
Pretty
do that.
bad.
Yeah, but I mean, I can make it work. Otherwise, I can just like get a
well,
conference room at work.
if we chose to do it that way, then that's not
Okay,
the,
that's
like,
cool. I'll just
standard way of doing it.
email.
It's
Yeah, we'll just
like-
see what works for everyone. Just that 8 to 9 slot is
How
already
the
reserved
data
for
is-
you. That is
Okay.
right.
Yeah,
Sounds good.
theoretically
Hi, Chris.
set out on
Talk
a bunch of
tomorrow.
computers
Good night.
and how it all connects to each other. So sometimes when we implement stuff, we change the way the algorithm works.
Thanks
so
for
that,
setting this up, by the way. I
like,
appreciate
with
it.
the goal
Yeah,
of
sure.
having the same results in the end, but we
Yeah, it's
change
very interesting
kind of
time.
like
It's actually very hard to
we
get
change
too
things
close
that can work in a distributed way. So that might be
Rail
one
sticker,
reason
you know,
why.
go
Open source is the way to go.
So anyway, actually, somebody who's wanting to
Oh,
sell
good.
Good,
version.
but I haven't found like the explanation to say, okay, this is how really.
Yeah, it's like I can
works.
show you what it
layers
does.
of my model.
I can show you the business value, but I can't tell you how we do any of
That's a
it.
good
So
question. That's a
yeah,
good
this
question.
is
I
a
think,
very, very unique opportunity here.
Yeah, it is.
yeah, I don't know.
Yeah, I see you decided to dress up for the occasion
Oh,
But
today.
if you,
Well,
if
usually
you,
actually,
Usually it's
actually
just the
very-
dress
wrote
shirt.
in
Yeah,
You added the blazer today.
Yeah, yeah.
Oops,
So
and
the
just
secret
ask
is I
that,
actually came back, I
somebody
went and picked it up from the dry
might
cleaner.
answer.
It's been there a long time, okay? Feel like they get
Because,
some
like,
violence.
All right,
I was
all
gonna
right,
say those
all
examples,
right.
But I think you
Yeah.
could go
Whatever
either
works
to,
there.
The
like,
conscience
the
thing was kicking in, be
stats,
friendly with
Stack
your
Overflow,
jacket.
where you're gonna ask for more theoretical
Oh
versions
man,
versus the
yeah,
code
jackets are
ones. You
jackets are
can either
hard.
post it there
First of all,
or
they're not cheap.
On the H2O stream,
and
but
then-
the only person
I
I know
didn't spend
is
more than like
this one
a
guy.
couple $100.
Okay,
Yeah,
okay.
You gotta treat them well.
I'm
My son
getting
wears
really
these
good results,
Hugo
but
Boss,
but
and
I
it's
need
like-
to explain
Yeah,
how.
yeah,
Because I'm using the autocontroller for protection.
I think we're of similar mind
And
here.
varying the weights
I mean, I'm
of
not
the
exactly
input
running up and down
using
Wall
the
Street.
controller, And then I use
My
those
son
weights
comes
to
me and
initialize
say,
a new
so they need to get
Oh,
some-
neural
they
network.
call them
Oh, cool.
pebble-
And basically
pebble
I'm not
going
having
down.
any
You know what
false
I'm talking about?
positives.
That's-
Like the
I'm
little
doing a
box.
really.
Oh
really
yeah,
good,
yeah, yeah.
That's awesome.
But
That's what
I
we
need to
pebble on here.
explain
Yeah,
That's it.
explain.
how.
It's like a little
That's
granular
good.
thing.
I mean, usually
look
if you
at
have
the
good
price and I'm
results, it
like,
takes
no.
longer.
It looks
Wow,
nice,
rather
it
than
feels
fast.
great.
Maybe you have some time.
But you know,
Yeah,
a
it's-
little
it's-
wallet
it's for
busting
amateur
here.
thinkers,
Just to go and do
so
it
I
anyway.
have to
So
be
you have
able
to
to
figure
explain.
out. Yeah.
It's $200
Yeah, I would just ask on the H2O stream. And then.
Oh man, I mean, unless you're like
I mean,
sure
probably
you're
the
gonna
person
nail
who
that
is
and be
written
making
it
like,
is not
you know,
gonna see it, so I
300K a
can just-
year or
See, they've
something
got
like
your tape
that.
measure, that's Hugo
Okay.
Boss,
Okay.
I'm not sure it's.
Okay.
That stuff is in his head.
But I gotta admit, it does feel
And then we'll
pretty
add it to
nice
the
to
doc.
have someone be like
Okay,
measuring you
okay.
up.
Thank you
and
so much.
I'll get you
Nice-
something
nice
that
to
fits
meet you.
exactly,
Bye.
and
Yeah.
it's just
Bye.
perfect and beautiful.
Yeah.
Hey Erin, appreciate you giving this talk. You're very interesting, very exciting. I actually did my undergrad in computer science on graphics and AI, so a lot of this, like, my senior project was actually developing an environment where students could, well, part of it, you could test a bunch of different AI things to see how well you performed, you get a score, and then one of the things I had to do at the end was how do you implement something to test machine learning.
Oh,
So
okay.
I've been interested since then.
So you're interested in like benchmarking maybe and stuff like that?
A
or-
little. Well, now
or how to
I've,
test that
I've
it's working?
switched from software development to marketing.
Okay.
It wasn't super my cup of tea
Uh-huh.
after a few years. But
Yeah.
actually now I work at a company, like I mentioned, we do AI-powered cloud infrastructure management.
Okay.
And so we have like some very rudimentary AI going on And actually, I think a lot of this stuff ties in very nicely to extra stickers. To where my CTO is trying to build our ML piece.
Okay.
So actually, he was going to be here tonight. Unfortunately, got pulled into something last minute.
Okay.
But I think he would be incredibly interested in this talk, and maybe
Yeah.
even like having a chat just to, I guess, what's the word I'm looking for? Match the brains. Like,
Yeah.
Pick your brain. That's what I'm looking for here.
Yeah.
Do you have like a business card or something? Some way I could have him contact
unlikely
you?
that I'll have
I think
one,
I
but-
shared his email, didn't I?
Yeah, is he
Oh.
the one that was on the
Yeah,
email?
I